All right, we're going to take a look at properties of functions here, and bear with me, there's quite a bit of writing. So what we see here is kind of like a computer, and that's how they reference a little bit of this input and output. So if we input a number, the machine, if you will, multiplies that number by 2, then it adds 3, and whatever comes out of that equation is your output. So for instance, if we put in 1, it multiplies by 2, which makes 2. We add 3, which makes 5, and that will be our output. Again, if we input 2, it multiplies by 2, which gives us 4. Adds 3, which gives us 7, and that's our output. So what is the rule for the input-output machine above? I wrote that the output is equal to our input times 2 plus 3. So which numbers would complete the table for this machine? I started with this input value that was missing its output. So if I input 4, we multiply by 2, that gives us 8. We add 3, and that will give us 11. Okay. Now, if we have the output and we need the input, we have to work backwards, and we need to do the opposite. So there's 2 ways we can do this in this question. If I have an output of 9, I need to do the opposite. So I need to subtract 3, which is 6, divide by 2, which is 3. So our input for this one will be 3. We can double check that if we wanted to. 3 times 2 is 6, plus 3 is 9. So that works. The mathematical way to show this would be putting in what we know for the output in our equation. So in the other case, we could have 13 is equal to some input times 2 plus 3. To solve for input, we need to do BEDMAS backwards. So we are going to subtract 3 from both sides. So we're going to take care of the addition statement by subtracting. So moving that over, we're going to get 10 is equal to the input times 2. Now to get the input by itself, we need to divide both sides by 2. So input equals 5 here. We could test that. 5 times 2 is 10, plus 3 is 13. Okay, some really key terms here. I'm just going to quickly type this out and then we'll talk about it. Okay, so in our first relation here, we'll define the domain, the range, and the function, and then relate it back. So the domain is the first set of elements in the relation. So those are usually our input values. We can also call them the independent variable or the x variable or x value in our graphs. So in our example above, our domain is, again, a set. So we're going to use our brackets here. And the values we could have in our input, again, also known as our domain, is 1, 2, 3, 4, and 5. Okay. Our range is the set of related elements. So the output values, we also call them the dependent value. They depend on our independent one. And they are the y value in graphs. So in our example above, the range was 5, 7, 9, 11, and 13. So a function is a special type of relation where each element in the domain is associated with only one element in the range. So for instance, something that would work is like 1 and 2, and then 2 and 2. So our elements within the domain, 1 and 2, are not repeated. So an example where this doesn't work, which I think helps to clear this up, would be 1, 2 again. But if 1 then points to 4, a different value, this doesn't work, okay? So if I were to plot this, I would have 1, 2, 3, 4, 2, 3, 4. 1 exists as 2 and 4, which doesn't work. Okay, so that's no good. However, 1 existing as 2 here and 2 existing as 2 is okay. So we can have the same values in our range multiple times, but we cannot have the same values in our domain multiple times. So each value in the domain is unique, and we'll come up with this again later, but it has to pass the vertical line test. So if I draw a vertical line anywhere on my graph, if 2 points are on the same vertical line, it is not a function. So for each relation below, determine whether it is a function, justify your answer, identify the domain and range of each relation that is a function. So a relation that associates the number with a prime factor of that number. If I search here, I have a domain of 4, range of 2, domain of 6, range of 2, domain of 6, range of 3. So we have the same domain value pointing to different range values. Therefore, this is not a function. We have one domain value with different range values. Again, that was this 6. Looking in our second one here, January has 31 days, February has 28 days, March has 31 days, and April has 30 days. Now, each of our domain values points to only one range value. Again, we can have a range value that is occupied by multiple domain values, but it cannot be the opposite way around. So this is a function because every value in the domain is attributed or attributed to a range value once. Okay, so we need to define the domain and range for this. So we will have the domain, again, it's a set, and we have January, February, March, April. And the range values, we have 28, 30, and 31 days. So again, 2 arrows to the same range value is okay, but 2 arrows from the same domain value is not okay to be a function. A dependent variable, a few more definitions here. A dependent variable is one that is the output or y value. It's listed second. In science, we would call this the responding variable. Again, a dependent variable is a variable whose value is determined by the value of the independent. So determined by the value of the independent variable. So, for example, the distance traveled on a road trip is dependent on the time spent traveling. Okay, so the dependent variable here would be the distance traveled. The independent variable would be time. The independent variable, again, is typically listed first in our tables. It is the input or x value. It is a variable whose value is selected or chosen. So value is selected or chosen and is not determined by another variable. So for instance, the best example of this is time. Time just continues ticking on and is not dependent on any other variable. Okay, so the table shows the cost of student bus tickets, C, in dollars, for a different number of tickets n. Why is this relation also a function? So the domain has distinct range values. We can see that 1 is attributed to 1.75, 2 to 350, 3 to 525, 4 to 7, and 5 to 875. We don't see that one domain value has multiple range values. So because again, the domain has distinct range values. Identify the independent variable and the dependent variable. So the independent is the one that does not depend on anything. So the independent would be the number of tickets, or n. The dependent would be the cost, or c. The range here, the domain and range, sorry. The domain is our independent variable. So that'll be our 1, 2, 3, 4, 5 tickets. And our range is the cost of values. So 175, 350, 525, $7, and $8.75. You can think of a function as an input-output machine. So the input can be any number in the domain, and the output depends on the input number. The output depends on the input number. So the input is the independent variable, and the output is the dependent variable. So again, going back to our chart here, our input was the number of tickets, the cost was the output. All right, function notation. Let's use this as an example for function notation. So our input, Q, we multiply by 25 to get our output. All right, so generally our output is equal to our input, and in this case, it is times 0.25. We have actual variables for our input and output in this case. So we can say that our output, V, is equal to our input, Q, times 0.25. Now, generally, we write that as 0.25Q. So we can say that V is a function of Q. V is a function of whatever Q is. V is dependent on Q. And therefore, if we are going to write function notation for it, we can say V of Q is equal to 0.25Q. So again, the function V depends on Q. So that's what this is saying. V is the dependent variable, Q is the independent variable. So again, function notation, we just write our dependent and independent together here. The equation C equals 25N plus 1,000 represents the cost, C, dollars, for a feast following an Arctic sports competition where N is the number of people attending. So A, describe the function. Write the equation as a function of a notation. So again, cost C is dependent on N, the number of people attending. So the function notation, we write C is dependent on N, which is equal to 25N plus 1,000. Really, the only thing that changes when we write this in function notation is we add the independent variable in brackets before the dependent variable, just showing what it is depending on. B, determine the value of C100. So C100 tells us that N is equal to 100. So we're going to put N100 in. So C100 is equal to 25 times 100 plus 1,000. So that is equal to 250 plus 1,000, which is equal to 1,250. This value represents the cost for 100 people to attend. So determine the value when C of n equals 5,000. And what does this number represent? So to do this, we need to set our entire equation equal to 5,000. And that'll equal 25n plus 1,000, sorry. So bed mass backwards here, we're going to look at our addition and subtraction first. So we need to do the opposite of our equation. So we're going to subtract 1,000 from each side, and we're going to be left with 4,000 is equal to 25n. To get n by itself, we now need to divide both sides by 25. And we get that n is equal to 160. So what does this number represent? This number represents the number of people that could attend for the cost to be $5,000. So a few discussion things. How can you tell whether a set of ordered pairs represents a function? Again, each domain value is unique. Okay, it does not have different range values attributed to it. When a function is completely represented using a set of ordered pairs or a table of values, how can you determine all of the domain and range of the function? Again, the domain is the elements listed first, or the independent variable. And the range values are listed second, and these are the dependent variables. Why are some relations not functions? Domain values could belong to more than one range value. So I drew a little example in my notes here. So if I have 1, 4, and 9, we could say that these are all perfect squares. And so they are the square of this set of values. So -3, -2, -1, 1, and 2. The problem here is that 1, the square root of 1 could be +1, or it could be -1. And the square root of 4 could be -2 or +2. In this value, I only have -3 for 9. So this is the relation is the square of. And again, the fact that 1 and 4 have two different range values for each makes this not a function. Why are all functions relations? Because all of the information in a function is related. So the relationship between sets is described in a function, therefore it must be a relation.